Hello HL, Ropke here. This is 1E, finding a quadratic from its graph. And again, this is a topic that will be expanded upon later on in the book, where we'll be finding equations of many different functions from their graphs, but we'll just start with quadratics. So we begin by assuming that the pictures we're looking at are quadratics, and that's an important point, but one that I don't want you to just overlook. So if this first one over here on the left is a quadratic, well, hey, I know what its x-intercepts are, so I should probably write down this one in factored form. So that gets me here. I need to remember that there might be a multiple here. Depending on what that multiple is, the x-intercepts will still always be -1 and 3, but the quadratic will stretch. So we need to figure out what that is. So we know that the y-intercept is 3, so I'm just going to set x equal to 0. I know that y is equal to 3, and that tells me that a has to be equal to -1, giving me a final answer here. Same idea with the one on the right. It just touches the x-axis at 2, so we start off with that as a repeated factor. So here's another one. We, again, know that one of the x-intercepts now is at -2. We don't know the other x-intercept, but we do know the axis of symmetry happens at 1. Since it's symmetrical, that means that it was 3 units to get from -2 to 1, which means it's going to be 3 more units to go over here. That's why my second root has to be 4. That gives me my factored form, and then the process is pretty similar to the last one. We're just going to find out the y-intercept. We know the y-intercept is 16, and that'll help us get the a value. Now, those examples, we're all doing it in factored form, but we could also do it in vertex form if the vertex was what we were given. So here I've got a vertex of 3, -2. So I fill in to vertex form here, it's going to be x minus 3. Remember to change that sign, squared, and then -2, that stays the same as that sign there. And then just like the last one, so I need to figure out what the a value is. It's the y-intercept in this case. So I set x equal to 0, y equal to 16. I figure out what a is. This other one starts the same way. The vertex is -4, 2. So we start off with x plus 4 squared plus 2. In this case, we don't know the y-intercept, but we do know an x-intercept. So we're told that when x is -2, y has to be equal to 0. So you can do it that way to figure out what the a value is. Of course, you could also deduce from this that the other intercept was going to be -6. And you could then say, well, that means that y is equal to a times x plus 6 times x plus 2. And you could work out the equation in factored form. And it'll be the exact same equation as this one here. No different. It's going to look different, but it's going to be the exact same quadratic. To do that, we would say 2 is equal to a times -4 plus 6, which is going to be 2, plus -4, excuse me, times -4 plus 2, which is going to be -2. So that means 2 is equal to -4. So that's going to be -1/2 is equal to a. Notice that is the a value from over there. I promise you, -1/2 times x plus 6 times x plus 2 should be the exact same quadratic as -1/2 times x plus 2 squared plus 2. Now, I said before, like we assume that these pictures are quadratics before we start. Generally speaking, when we have a function of an even degree, it can look relatively quadratic. So here I just graph 4 functions. X squared plus 1, that's pretty simple. We know what that looks like. Notice here x to the 4th minus 1. It still has the same vertex. It still has the same x-intercepts as x squared minus 1. But it kind of looks like it's getting like a little flatter down there at the bottom. And that pattern continues as the exponent rises. In x to the 6th minus 1, it's getting very flat as we get near the vertex. And when I graphed x to the 50th minus 1, I mean, it just looked almost like right angles down there. So they all basically have the same shapes in this case. Um, but were I to do this problem, I would assume that it had to be a quadratic because if it was one of the more complicated ones, it could be very challenging for me to work out exactly what it is. Don't worry about this. You're not going to be tricked um, into writing it out as a quadratic when it's really quartic, unless you've missed something super obvious. But more on that in chapter 6. Just a few more words I wanted to say about this. Quartic equations such as this could actually turn around quite a few times, or it might look something like that. Something a 6th degree polynomial could turn around 1, 2, 3, 4, 5 times, or have some other weird shape. And this one, I'm not going to draw this last one, but it could have a lot more humps. Now that's going to require it to have more terms. So this first one would need like an x cubed or an x squared or an x term as well. And this one would need an x to the 5th term and an x to the 4th term and so on down the line to really get like all of the turns happening. But in general, these shapes won't look just like parabolas. And the other thing I wanted to say was like, why does it get flattened out like that? Well, what's happening here is, let's think about what happens to a number when we raise it to the power of 50. So if I choose a number that's bigger than 1 and I raise it to the power of 50, it's going to get huge really, really, really fast. So the reason that this looks like it's a vertical line is it's not. It's just that when I take the number 1.0001 and I raise it to the power of 50, I get something like surprisingly large. Let's actually see. 1.001 to the power of 50. Okay, that was less exciting than I expected it to be, but hey, let's do 1.5 to the power of 50. Oh, okay, there we go. So it does grow very, very, very fast. So that's why it looks like it's going up essentially vertically, because it's rising much faster than, say, this first example was. And likewise, as when we square or cube or whatever a number that's less than 1, it gets smaller, right? So if I take 1/2 and I square it, I get 1/4. But if I take 1/2 and I raise it to the power of 4, I get 1/16, which is even smaller. And if I take 1/2 and I raise it to the power of 50, I have no idea. I get, okay, so that's basically 0. So that's why very, very rapidly, as we move to the left of 1, the numbers, the output values here are essentially going to be, well, it's at -1 because I'm basically getting a 0 from the raising it to the 50th, and then I'm subtracting 1. So that's why those shapes are what they are. So that's it for this section. This is a topic, as I said, that really gets more challenging and interesting when we're dealing with higher degree polynomials. We'll worry about that when it happens later.